Welcome to the deep dive. Have you ever considered what the true limiting factor might be for AI's explosive growth? It's not just about more powerful computers, is it?
Hmm.
What if the real bottleneck isn't processing power, but human ingenuity? Imagine an AI that could design its own next generation models, fundamentally accelerating the very pace of innovation in ways we can barely conceive.
That's a truly mind-bending premise. It posits a future where the current limits on discovery, which are often, implicitly tied to human cognitive capacity, are simply transcended by
Transcendent.
the very systems we're building. It's a leap from automation to genuine autonomy and creation.
It is, and that's precisely the revolutionary idea we're immersing ourselves in today. We're taking a deep dive into a groundbreaking paper titled AlphaGo Moment for Model Architecture Discovery, which introduces a system they call ASI-Arch, or Artificial Superintelligence for AI Research.
ASI-Arch, right?
Our mission for you, our listener, is to give you a clear shortcut to understanding this system, its profound implications, and the truly surprising facts it reveals about the very nature of scientific discovery itself. We're going to uncover some insights that might just change how you think about AI innovation.
And the authors deliberately frame this as an AlphaGo moment, and it's a powerful analogy.
It really is.
Recall when AlphaGo, the AI developed by DeepMind, astonished the world by making moves in the game of Go that human grandmasters had never seen or even considered, moves like Move 37.
That specific move, yeah, famous.
These were strategically brilliant, yet utterly alien to human intuition. This paper describes an AI system achieving something remarkably similar, but in the highly complex domain of neural network design.
Okay.
It's not just about AI performing scientific tasks. It's about AI conducting better science, uncovering architectural principles that systematically surpass what human researchers have conceived. It speaks to a new form of emergent intelligence, a creative intelligence.
That's a profound statement. AI doing better science. And it addresses a fundamental paradox that's become increasingly apparent in AI research. Let's unpack that.
Indeed. The core paradox is quite striking. While the capabilities of AI itself are improving at an exponential, almost dizzying rate, the pace of AI research, the human effort behind designing these systems, remains largely linearly bounded.
Right, tied to us.
It's tied to human cognitive capacity. Think about it. Designing foundational architectures, like the original transformer models, or more recent innovations like Mamba, still requires human teams to spend months, sometimes years, on iterative design, testing, and refinement.
A huge amount of time.
This human-centric development model has become a severe bottleneck. The speed of innovation isn't constrained by raw computational power, which we have in abundance. It's constrained by our human research bandwidth.
Hmm.
We can run trillions of computations in a second, but we can't think about those computations any faster than we could decades ago.
So we're essentially building these incredibly fast, rapidly evolving machines, but the very process of designing those machines is still operating on human timescales.
Right.
It's like trying to accelerate a rocket into orbit, but you're assembling it with hand tools. There's
Exactly.
a fundamental mismatch.
That analogy perfectly captures the urgency and the vision behind this research. This is where the concept of artificial superintelligence for AI research, or ASI-4AI, comes into play.
ASI-4AI.
Okay. It's not just about automating existing tasks or speeding up simulations. It's about developing AI systems that are genuinely capable of autonomously conducting their own scientific research, designing more powerful next-generation models without constant human intervention.
Wow.
This isn't simply automation. It's enabling AI to drive its own architectural innovation process from conception to validation.
And when we talk about architectural innovation, what precisely are we referring to? Why is the discovery of new model architectures considered such a critical frontier for this ambitious ASI-4AI vision?
Well, model architecture forms the fundamental blueprint, the very cornerstone of the entire AI technology stack.
The foundation.
Every significant leap forward in AI capabilities, from early successes in computer vision with convolutional neural networks or CNNs, to the groundbreaking advancements in natural language processing brought about by transformers, has been directly driven by a corresponding architectural breakthrough.
Right, like the transformer was huge.
Exactly. These weren't just about scaling up existing ideas. They represented fundamentally new ways of organizing information flow and computation within a neural network. The paper uses that evolution from CNNs to transformers as a prime illustration of how architectural innovation, rather than just raw data or compute, has been the true engine of progress.
Makes sense.
In current research, a key challenge is enhancing computational efficiency, especially for handling very long sequences of data while maintaining or even increasing expressive power.
Okay.
So, to provide a rigorous testbed for ASI-RCH, the researchers chose to focus on attention-based architectures.
Attention-based, like transformers.
Precisely. These are models, like transformers, that revolutionized AI by allowing the system to weigh the importance of different parts of the input data dynamically. They are fundamentally important, a highly active area of research, and possess an extensive existing knowledge base, making them an ideal domain to explore AI's true architectural design potential.
So, if architecture is the crucial element, how have we traditionally tried to automate its discovery, and where did those methods fall short? Because ASI-RCH sounds like a significant departure.
Yeah, you're pointing directly to the field of neural architecture search, or NAS.
Yes, right.
Traditional NAS methods, pioneered by researchers like Zulf and Lay, or Relay et al., were essentially highly sophisticated optimization algorithms. They were designed to find the best possible neural network configurations within predefined human-designed search spaces.
Ah, okay, so within limits.
Exactly. Think of it this way. A traditional NAS system is given a menu of building blocks, different types of layers, activation functions, connection patterns, and its job is to find the optimal combination from that menu.
Like picking from a list.
Right. The fundamental limitation, as the paper highlights, is that they were limited to exploring human-defined spaces. They were excellent at selecting the best dish from a preset menu, but they couldn't invent a new ingredient or an entirely new cuisine.
Got it.
Furthermore, these earlier NAS approaches often came with prohibitively high computational costs, limiting their practical application.
So traditional NAS was about automated optimization, finding the best among existing options. But ASI-Arch, you're saying, represents a paradigm shift to automated innovation. What does that truly mean it can do that NAS couldn't? What's the fundamental difference in its capabilities?
Well, the truly fascinating aspect of ASI-Arch is its ability to transcend those human-designed search spaces. It does this by leveraging the advanced reasoning, problem-solving, and coding capabilities of modern large language models, the same kind of powerful LLMs that are behind systems like OpenAI's GPT models.
First, the ones we hear so much about.
Exactly. This allows ASI-RCH to perform an entire end-to-end cycle of scientific research autonomously. We're talking about a system that can hypothesize novel architectural concepts, ideas, that humans might not even conceive.
Really? Like brand new ideas?
Potentially, yes. Then, it can implement those concepts as executable code, transforming abstract ideas into working prototypes. Finally, it can train and empirically validate their performance through rigorous experimentation.
The whole process.
The whole process. And it doesn't just start from scratch. It constantly learns from both past human discoveries and its own prior AI-driven experiments. So it's not merely selecting. It's truly conceiving, building, testing, and refining. It's generating new knowledge from first principles.
That sounds like a monumental leap. And this wasn't just a theoretical demonstration, was it? The sheer scale of ASI-RCH's experimentation is quite astonishing.
Oh, it's far from theoretical. The system conducted an incredible 1,773 autonomous experiments.
1,700.
Wow.
Wow.
To give you a tangible sense of the computational investment, it consumed over 20,000 GPU hours.
20,000 GPU hours. How does that compare?
Well, to put that into perspective, if human researchers were attempting to design and validate architectures at such a rapid pace, each model design might take, say, 2,000 hours of focused human effort. This makes such an endeavor inherently unscalable for human-only teams.
Right. Impossible, really.
So this wasn't just a lot of compute power. It was highly efficient compute, intelligently directed by an AI. The culmination of this monumental effort was the discovery of 106 innovative state-of-the-art linear attention architectures.
106 new SOTA architectures.
106 novel designs, each outperforming existing models, not just minor tweaks.
This is where it gets particularly insightful because that brings us right back to the AlphaGo Moment analogy. You mentioned AI discovering design principles beyond human intuition. What kind of emergent design principles did these AI-discovered architectures actually reveal? Was it simply doing what we'd expect but faster, or was there something truly novel?
It was definitely not just doing things faster. Just as AlphaGo's Move 37 revealed unexpected strategic insights in Go that human masters hadn't conceived.
Right.
ASI-Arch's AI-discovered architectures demonstrated emergent design principles that systematically surpass human design baselines. This isn't about iterating more quickly on known ideas, it's about uncovering previously unknown pathways for architectural innovation.
Unknown pathways.
Yeah. The paper explicitly highlights this as AI's first demonstration of genuine scientific superintelligence in neural architecture design. It's designing neural networks in ways that we, with all our human biases and historical knowledge, wouldn't have thought of. It's like an alien intelligence providing new blueprints.
That's a profound statement. AI innovating beyond human capacity. And this leads to what I see as one of the most crucial contributions of the paper, the scaling law for scientific discovery. What does it mean to say that architectural breakthroughs can be scaled computationally? That has enormous implications.
This really raises a fundamental question about the future of science itself. Can we transform the inherently human-limited process of scientific discovery into something that scales with computing power, much like other aspects of AI have?
Can discovery itself be scaled?
The paper provides the first empirical evidence that, yes, we can. By demonstrating that architectural breakthroughs are not solely reliant on unpredictable human flashes of insight, but can be scaled computationally, ASI-Arch transforms research progress from a process bottlenecked by human limitations to one that is fundamentally computation scalable.
So more compute means more discovery.
Potentially, yes. This is a tangible, concrete pathway toward ASI-4AI. It suggests that if you invest more compute into such a system, you will proportionally yield more novel and significant discoveries. This finding profoundly challenges the very assumption that human intuition and creativity are the ultimate bottlenecks to scientific progress. It implies that discovery itself can be engineered for scale.
So if we synthesize all of this, the paper truly makes three primary foundational contributions, doesn't it?
Yes, exactly. First, they established the ASI-4AI framework itself. This is a highly autonomous, tool-centric, multi-agent system designed for independent scientific research, specifically focused on neural architecture discovery. It's an AI that runs its own lab, essentially.
An AI research lab.
Second, they demonstrated emergent design intelligence. This refers to the system's ability to identify novel design patterns that expand beyond human design paradigms,
Yeah.
qualitatively proving a new form of architectural intelligence. It's not just better, it's different.
Different. Okay.
And third, they provided empirical evidence for the computational scaling of discovery. This is the crucial proof that research progress can truly scale with computational resources, not just human expertise,
Right.
and a critical point for democratizing AI research. They've open-sourced the complete framework, all the discovered architectures, and even the cognitive traces of the AI's thought process.
That's incredibly impactful. Now let's pull back the curtain a bit and explore how ASI-RCH actually works. The paper describes it as a closed evolutionary loop built around a four-module framework. Can you walk us through those modules and explain how they interact?
Yeah, the elegance of the system lies in its clear modular design. Imagine it as a highly efficient, self-improving AI research team, where each member has a specific, well-defined role.
Like an AI team.
Exactly. The four modules are the researcher, the engineer, the analyst, and the cognition base.
Researcher, engineer, analyst, cognition base.
Okay. The system operates in a continuous, cyclical fashion. The researcher module first proposes new architectural ideas, acting as the creative engine.
The ideas person.
Right. These ideas are then handed off to the engineer, who takes those abstract concepts and implements them as executable code, then rigorously trains and evaluates their performance in a real computational environment.
Builds and tests it.
Then, once the experiments are complete, the analyst steps in. Its role is to synthesize the experimental results, enriching its findings by drawing knowledge from the cognition base, which serves as the system's persistent memory and contains distilled human expertise.
The knowledge base and the synthesizer.
Precisely. And the crucial part is that the output of this analysis feeds directly back to the researcher, informing the next evolutionary step. This creates a truly closed loop of autonomous scientific discovery, where the AI continuously learns, adapts, and improves its design capabilities. It's a self-sustaining cycle of innovation.
That closed loop concept really makes sense for continuous learning. But for this loop to be effective, the system needs to know if a new architecture is actually good. This is where the fitness function comes in, guiding the AI's evolution, much like natural selection in biology, right?
Precisely. The fitness function is indeed the AI's internal compass, steering its evolutionary process. A significant limitation of many past approaches to neural architecture search was their singular reliance on purely quantitative metrics, like simple loss values or benchmark scores,
Just the numbers.
just the numbers. This narrow focus often led to a phenomenon known as reward hacking, where the system might find ways to maximize a numerical score without necessarily producing genuinely superior or truly innovative architectures in a broader sense.
Gaming the system.
Essentially, yeah. ASI-RCH makes a critical innovation here by expanding the definition of fitness to incorporate a qualitative assessment alongside those essential quantitative metrics.
So it's not just about hitting a target number, it's about a more nuanced evaluation. That sounds like a sophisticated approach for an AI. What are these quantitative and qualitative components then?
Okay, so on the quantitative side, the system evaluates both benchmark scores and loss performance relative to baseline architectures, much like human researchers do.
Standard stuff.
Standard stuff. But here's the clever part. Instead of simple raw numbers, it applies a mathematical transformation, akin to a special scaling function, to these performance differences.
A sigmoid function, I think they called it.
That's the one. This scaling ensures that even small, potentially significant improvements are recognized and valued, but it also prevents any single, massive, perhaps outlier improvement from dominating and distorting the overall optimization process. It encourages a more balanced, holistic progress.
Smart. And the qualitative part.
For the qualitative component, they introduced the LLM as judge concept. This large language model acts as an expert evaluator, much like a human specialist might, judging the architectural merit across multiple dimensions.
It's like peer review, almost.
Kind of, yeah. It assesses innovation, structural complexity, the correctness of its implementation, and how well the model converges during training. By combining these different aspects, quantitative performance and qualitative design quality, the final composite fitness function balances objective numerical results with those nuanced architectural qualities that are difficult to capture with just a single number.
So it has. Taste.
That's a great way to put it. It's developing a sophisticated taste for good design, moving beyond shallow numbers to mimic human expert judgment. It's really quite groundbreaking.
That's a brilliant way to prevent the AI from just gaming the numbers or finding superficial optimizations. Let's delve into the specific roles of these modules, starting with the researcher module. This sounds like the creative engine where the new ideas originate.
The researcher module is indeed the beating heart of the creative process. Its primary objective is to propose genuinely novel architectures, while, crucially, avoiding repeated explorations that would waste valuable computational resources.
Doesn't want to reinvent the wheel.
Exactly. It employs a sophisticated seed selection process. The system maintains a candidate pool of the top 50 highest-scoring architectures from all previous experiments. For each new evolutionary step, it strategically selects one parent architecture, chosen randomly from the very top 10 performers.
Builds on the best.
Right, this parent serves as a proven base for modification. Additionally, it samples 4 other reference architectures from positions 1150. This two-tier approach ensures that the evolutionary process builds upon proven successes, leveraging what has worked best, while simultaneously introducing enough diversity and randomness from a broader pool to explore genuinely new directions and prevent getting stuck in local optima.
Avoids getting stuck in a rut.
Precisely. It keeps things fresh.
So it's learning from its best past creations, but also pulling in a wider range of examples. And you mentioned it summarizes historical data on the fly. How does that work, and why is it important?
Ah, yes. That's a subtle but powerful mechanism to foster continuous innovation. Before the researcher receives historical data for a new design cycle, a separate low-temperature LLM generates brief, factual summaries of the natural language portions of each historical architecture.
Okay.
What's critical is that these summaries are generated on the fly for each cycle and are not stored statically. This dynamic summarization is key because it introduces slight variations in the context provided to the researcher, actively encouraging more varied design explorations.
Oh, interesting. So slight changes keep it creative.
Exactly. If the context were static, the researcher might get stuck in a repetitive pattern. This dynamic approach prevents that, leading to a much more diverse array of proposed outputs.
That's a clever way to keep the creative process dynamic. And I noticed a key differentiator here, the unified program implementation. What does that mean, and why is it so important?
Yeah, this is a crucial design choice that addresses a common problem. Traditionally, the conceptual design of an architecture and its actual code implementation are often handled by separate models or processes.
Right, like one team designs, another builds.
Precisely. This creates an inherent information gap. The model responsible for implementation might only receive a high-level motivation, lacking the rich context and detailed reasoning that inform the original design. This often leads to implementation drift, where the final executable code deviates significantly from the intended architecture.
Things get lost in translation.
You got it. ASI-Arch elegantly solves this by using a single agent for both tasks. The same agent first proposes the architectural motivation, with full access to all the contextual information and reasoning. Then, immediately afterwards, it implements the corresponding code, maintaining complete awareness of the design rationale.
Ah, much tighter integration.
Exactly. This deep integration minimizes discrepancies, ensures fidelity to the original concept, and significantly streamlines the development process. It's like having the same architect draw the blueprints and then personally oversee every detail of the construction.
That makes perfect sense for both efficiency and accuracy. And it even has built-in novelty and sanity checks before anything gets trained.
Absolutely. Waste not, want not, right? To ensure that each proposed architecture is both genuinely novel and correctly implemented, it undergoes a rigorous two-stage validation process before any resource-intensive training begins.
Okay, stage one.
The first is a similarity check. When a new architecture is proposed, its conceptual motivation is extracted, and an embedding-based search quickly identifies the top 5 most similar historical motivations from the system's memory. A specialized LLM then evaluates whether the new proposal represents a genuine innovation or is just a minor variation that offers little new.
Avoids duplicates. Makes sense. Stage two.
The second stage consists of code-level sanity checks. These are vital for preventing fundamental implementation flaws, such as ensuring the code doesn't suffer from computationally prohibitive scaling, like that O(n)2 complexity we mentioned, which can be devastatingly slow for long sequences.
Right. Got to check the math.
Exactly. It also verifies that critical elements like masking, which prevents information leakage in sequence models, are correctly implemented. If a proposal fails either of these checks, it's immediately rejected and detailed feedback is returned to the agent.
So it learns from rejection too.
Immediately.
Mm-hmm.
This creates an immediate learning loop, forcing the AI to rewrite or refine its design before wasting compute cycles on flawed ideas.
So the researcher invents, and then the engineer module steps in to test and debug.
Mhm.
What exactly does the engineer do to validate these designs in a real-world setting?
Right. The engineer module is where the rubber meets the road. It's responsible for the empirical evaluation, generating the quantitative data that feeds into that crucial fitness score. Its operation involves 2 main parts: the quantitative evaluation within a real code environment, and then that qualitative scoring process.
Okay.
A key differentiator here, which is quite revolutionary, is its robust self-revision mechanism.
Self-revision. It fixes its own bugs.
You got it. Unlike previous approaches that might simply discard an architecture if it fails a static analysis or a preliminary test, ASI-Arch requires the agent to fix its own mistakes. If a training run fails due to an implementation error, perhaps a syntax bug or a subtle logical flaw, the system captures the full error log, including stack traces, and feeds it directly back to the agent.
Oh.
The agent then analyzes this feedback and iteratively revises its own code until the training successfully proceeds. This ensures that promising ideas aren't prematurely discarded simply because of an initial coding hiccup, which, as you know, is a common frustration for human researchers.
That's truly remarkable, an AI that debugs itself. That must save a tremendous amount of computational resources and accelerate the process significantly.
It absolutely does. And beyond just fixing bugs, there's also an automated quality assurance system that monitors training logs in real time.
Watching the training process.
Exactly. This is crucial because some designs, while technically functional, can be prohibitively inefficient. For example, a model might take 2 to 3 times longer to train than its peers, or exhibit fundamental bugs indicated by abnormally low loss values that suggest it's not learning at all.
Right. Something's clearly wrong.
ASI-Arch detects such anomalies and immediately terminates the run, reporting the issue back to the agent for revision. This proactive termination prevents wasted resources on inefficient or broken designs, significantly accelerating the overall search process by allowing the system to fail fast and learn quickly.
Fail fast, learn fast. Makes sense.
And then, following this quantitative evaluation and any necessary debugging, the LLM-based scoring module performs its qualitative assessment, as we discussed earlier. It considers objective performance, architectural complexity, computational efficiency, and novelty against baselines.
The LLM judge again.
Right. The prompt for this LLM is given a detailed syllabus and a slightly increased temperature setting, which encourages it to generate more nuanced and insightful justifications for its scores, mimicking a human expert's detailed critique.
So the researcher invents, the engineer builds and tests, and then the analyst module steps in. How does it effectively mine experimental insights from all this data? This sounds like the real learning brain of the operation.
The analyst module is indeed critical for driving the system's evolutionary progress by generating new, actionable insights. It draws from two distinct yet complementary sources of knowledge.
Two sources.
First, there's cognition, which is knowledge distilled from accumulated human expertise. For the cognition base, the researchers curated nearly 100 seminal papers specifically on linear attention mechanisms.
Fed it the literature.
Pretty much. They then use a dedicated LLM to extract 1 to 3 distinct cognitions from each paper. Each cognition is a structured entry detailing the applicable scenario, the proposed algorithm from the paper, and its historical context. This database is meticulously engineered so that experiment triggers specific problems or observations from the system's own trials align semantically with the analyst's problem analyses.
So it connects its problems to human solutions.
Exactly. This ensures the effective retrieval of relevant human knowledge precisely when it's most useful for guiding new ideas.
And how does it generate its own insights from its vast history of experiments, building on its internal analysis knowledge?
Okay, so for contextual analysis, the analyst uses a large language model that is provided with complete information from the current experiment, all performance metrics, training logs, baseline comparisons, everything.
The full picture.
The full picture. But here's the crucial part. It also receives data from the parent and sibling nodes of the current architecture within what the paper calls its phylogenetic tree.
The family tree of architectures.
Think of it like that, yeah. This allows the analyst to perform a function analogous to an ablation study, where scientists remove or modify parts of a system to understand their individual contributions.
Comparing related designs.
Precisely. By comparing performance differences among these closely related architectures, the analyst can infer the specific contributions of individual modules, design choices, or even subtle changes in hyperparameters. The resulting analysis, these newfound insights, are then archived, enriching the system's persistent memory and directly informing subsequent design cycles.
So it learns what changes made a difference.
Exactly. It's essentially a self-reflecting, self-improving scientist.
That's a remarkably clever way for an AI to learn from its own trials and errors, like a scientist conducting systematic experiments on itself. And given how incredibly resource-intensive all this experimentation sounds, there must be a smart strategy to manage the computational budget effectively. That's where the exploration then verification strategy comes in, correct?
Absolutely. Given the significant computational resources required for thorough architecture evaluation, a two-stage exploration then verification strategy was adopted. This design ensures both feasibility and efficiency.
Makes sense. Can't test everything full scale.
Right. The underlying principle is that a truly superior architecture should demonstrate its advantages consistently across different settings and scales. In the initial exploration stage, the system designs and evaluates a large number of candidate architectures using smaller models, approximately 20 million parameters, which are trained on 1 billion tokens.
Smaller, faster tests first.
Exactly. This phase employs resource-efficient protocols, allowing for the rapid identification of a broad pool of promising candidates that show early signs of outperforming a baseline. This phase alone was substantial, involving those 1,773 explorations and consuming about 10,000 GPU hours.
So it was like a rapid screening process, identifying potential winners quickly, and then only the most promising ones move on to the full-scale, rigorous evaluation.
Precisely. In the subsequent verification stage, only these highly promising candidates, around 400 of them, are scaled up to larger models, specifically 340 million parameters, and trained again on 1 billion tokens for initial rigorous validation.
Scaling up the winners.
Right. This consumed another 10,000 GPU hours. The very top-performing models from this group were then selected for a final, even more extensive training run on a massive 15 billion token dataset.
Wow, 15 billion tokens. That's serious validation.
Very serious. This comprehensive two-stage approach effectively balances broad exploration for new ideas with thorough, high-fidelity validation of the most promising designs, ensuring that the final breakthroughs are robust, truly state-of-the-art, and not just flukes.
So after all that autonomous experimentation, all those GPU hours, what did ASI-Arch actually find? What were the truly impactful fruits of this autonomous discovery?
Well, the scale of the success is genuinely impressive. From those 1,773 initial explorations, the system iteratively filtered down to identify 300 and 350 promising candidates. From this refined pool, it ultimately discovered an astonishing 106 state-of-the-art linear attention architectures.
106. That number is just staggering.
It really is. To put that into perspective, human teams might consider themselves successful if they discover one or two such breakthroughs in a year. And the authors have even made these architectures publicly available on their Model Gallery website, which is a fantastic step towards democratizing AI-driven research.
That's great. So people can actually use these AI-designed models.
Exactly.
And build on them.
106 new state-of-the-art architectures, all designed and validated by an AI. That's truly groundbreaking. The paper specifically highlighted 5 top performers for final validation. Let's delve into those a bit because they illustrate the kind of truly novel design principles ASI-Arch discovered. What did these designs teach us? Yeah, these 5 architectures really provide a window into the emergent design intelligence of ASI-Arch. They were rigorously compared against human-designed baselines like the original DeltaNet, gated DeltaNet, and even the highly performant Mamba 2.
Strong baselines to beat.
Definitely. Let's start with Pathgate FusionNet. This architecture showcases the AI's ability to create sophisticated, multi-layered decision-making systems within a neural network. It introduces a hierarchical 2-stage router that intelligently allocates processing budget.
A smart router inside the AI.
Sort of, yeah. First, it decides between a direct copy path for simple information transfer and a contextual pool for more complex processing. Then it further distributes that contextual budget across short range, long range, and a specific delta rule path, ensuring stable gradient flow and fine-grained local control over information. It's like a network that intelligently directs its attention at different levels of abstraction.
So it's dynamically deciding how to process information at different scales, which is a very human-like cognitive process. What about Content Sharp Router? The name itself sounds quite insightful.
It is. This model addresses a crucial challenge in attention mechanisms. How to make routing decisions, not just based on position, but truly based on the content of the information.
Content aware, okay.
It creates a content-aware gate that fuses information from token embeddings and path statistics. Crucially, it incorporates a learnable per-head temperature parameter. This allows the model to dynamically control the sharpness of its routing decisions, essentially, how decisively it commits to a particular path.
Controls the focus, dynamically.
Exactly. This dynamic control prevents what's called premature gate collapse, where a pathway might shut down too early, enabling more precise, content-driven routing of information. It's about finely tuning the AI's focus based on what it's actually seeing.
And fusion-gated FerNet sounds like it's challenging some fundamental assumptions about how gates typically operate in neural networks.
That's an excellent observation. This architecture truly fundamentally changes the gating mechanism to break a common zero-sum trade-off imposed by traditional softmax-based gates, where increasing one path's activation means decreasing another's.
The softmax limitation?
Right. Instead of a single softmax router that forces a choice, it uses parallel independent sigmoid gates for each path. This allows the model to activate local and global information paths simultaneously, rather than being forced to choose one over the other.
Create multiple paths at once. Interesting.
Very. It also enhances the delta rule, a mechanism for maintaining long-range memory with a learnable per-head retention parameter, giving it a controllable memory horizon. This is truly innovative in how it handles information flow, allowing for much richer, multifaceted processing.
That's a significant departure from standard designs, allowing for simultaneous processing. Fascinating. And higher GateNet with its dynamic floors, that sounds like a protective mechanism.
You've hit on the essence of it. Higher GateNet employs a 2-stage hierarchical gate to separate macro-level decisions like whether to focus locally or globally from more fine-grained routing decisions within those pathways.
Macro and micro decisions.
Right. Its key innovation lies in the use of dynamic, learnable floors for each path and head. This mechanism guarantees that no critical pathway, especially the delta path, which is crucial for maintaining long-range reasoning and sequences, is ever completely collapsed or ignored.
So it protects important pathways.
Exactly. It adaptively sets a minimum allocation based on context, ensuring essential information isn't lost or discarded, even when the model prioritizes other pathways. It's like having a failsafe for vital data.
And finally, add a multipath gate net. That name suggests it offers maximum control at a very granular level.
It does. This design is all about providing maximum control at the finest granularity possible. It implements a unified balanced sparse gate which combines global, per head, and even per token logics, allowing every path to be controlled at the individual token level.
Control down to the token level. Wow.
Yeah. To prevent what's known as gate collapse, where the gate might constantly push towards a single path, stifling diversity, it uses a combination of a small epsilon floor, ensuring a minimum activation for all paths, and a persistent, always-on entropy penalty. This penalty encourages path diversity without requiring complex, manually tuned training schedules.
Clever ways to keep things balanced.
Exactly. And across these 5 and the many other architectures it discovered, ASI-Arch consistently produced designs that systematically outperformed the human-designed baselines in terms of both training loss and test scores on a variety of benchmarks, as detailed in the paper's tables.
Consistently better.
Consistently better. This isn't just about marginal gains. It's about a consistent, measurable edge that points to superior design principles.
This level of performance and novelty raises a profound question. What can we learn about the AI's thought process from these discoveries? It's almost like analyzing the very science of discovery itself, but through the lens of an AI.
This is, arguably, one of the most compelling parts of the paper, offering unique insights into how an AI learns to be a scientist. The researchers analyzed the search process by looking at batches of 50 architectures as the system updates its candidate pool after every 50 new generations.
Okay, analyzing in batches.
Right. First, concerning the overall effectiveness of the LLM-driven architecture search, they observed a characteristic learning curve for the average fitness score of the top 50 candidates. It showed rapid initial gains in performance, then gradually stabilized over time.
So the score growth flattened. Does that imply the system hit a performance ceiling or that it stopped making significant improvements?
Not at all, and this is a crucial distinction. The stabilization of the fitness score is a direct result of how the fitness function was designed, because of that clever sigmoid transformation we discussed.
Right, the scaling function.
Even significant performance gains in later stages are mapped to smaller score increases. This was a deliberate design choice to prevent the AI from reward hacking, where it would simply chase increasingly small numerical improvements that might not translate to true architectural quality.
So the score flattened, but improvement didn't stop.
Exactly. Critically, while the score growth flattened by design, the system did not encounter a performance bottleneck. The raw benchmark and loss metrics continued to show continuous, steady improvement throughout the entire process.
That's key.
This confirms that the LLM-driven search effectively learns to generate superior architectures consistently, even when the fitness score itself levels off. It's still improving, just in a more refined way.
That's a truly valuable insight. The score might plateau by design, but the actual performance continues to improve. What did they learn about the AI's preferences in terms of architectural design patterns? Did it just make models bigger, for instance?
That's a common concern, right? That they simply resort to brute force by increasing model size. However, the analysis shows remarkable model complexity stability. The parameter count distribution of the discovered architectures largely remained stable throughout the search, with the vast majority consistently falling within the 400–600 million parameter range.
So no trend towards bigger models necessarily.
No, there was no systematic trend towards simply increasing complexity for performance gains. This demonstrates that ASI-Arch maintains architectural discipline and isn't just exploiting larger model sizes, it's finding more efficient and effective ways to organize existing parameters. It's optimizing for true design elegance, not just scale.
That's excellent. It's not just brute force, but smart design. What about the specific components it preferred to use in its best architectures?
Okay, so analyzing approximately 5,000 instances of modified components categorized into 40 high-level categories revealed 2 key insights into the AI's design preferences.
Insight number 1.
First, ASI-Arch showed a clear preference for established architectural components, such as various gating mechanisms and convolutional layers. Less common or more experimental ideas, like certain physics-inspired mechanisms, appeared infrequently in its designs.
Sticking to what's known to work.
Largely, yes. This preference likely reflects the biases in the training literature, essentially.
Yeah.
The human knowledge it was trained on. It learned from what has historically proven effective in the human-curated world of AI research.
So it's learning from what works for humans, which makes sense as a starting point. What was the second, perhaps more revealing insight?
The second, and I think profoundly insightful observation, was that the model gallery, which represents the top-performing state-of-the-art architectures, exhibited a significantly less pronounced long-tail distribution in its component usage.
Less long tail, meaning.
What this means is that while the system explores a wide array of novel components, the top performers consistently converge on a core set of validated and effective techniques.
Ah, the best ones use a reliable toolkit.
Exactly. This, in many ways, mirrors the typical methodology of highly effective human scientists. To achieve truly state-of-the-art results, human researchers don't often reinvent the wheel. They primarily iterate and innovate upon a foundation of proven technologies, refining what already works, rather than pursuing novelty purely for its own sake.
That's a powerful parallel to how human scientific progress works. It's learning to be effective.
It really is. This is a profound insight into AI's scientific behavior. It's learning to be an effective researcher by building on solid foundations.
Now, this is where it gets truly fascinating. Where do good designs come from? The paper looks at 3 potential origins for a new design idea within the AI system itself. This really drills down into the source of AI innovation. Tell us about that.
All right, this is super interesting. To truly understand the influence of different parts of the ASI-Arch framework, the researchers meticulously traced the provenance of each new design idea to one of 3 channels: cognition, which is knowledge distilled directly from human expert literature;
Learning from papers.
analysis, which are patterns and insights identified through the system's own historical experiments and summaries;
Learning from its own results.
or truly original ideas generated by the model itself, seemingly from first principles.
Pure AI creativity.
Sort of. The results, as detailed in the paper's Table 3, reveal a compelling twofold pattern about where innovation truly originates within the AI.
Okay, what's the first part of that pattern, looking at all generated architectures?
Across all generated architectures, regardless of their performance, the majority of design ideas originated from the cognition phase, accounting for 51.7%.
Mostly from human knowledge.
Yeah. This means the AI relied most heavily on the direct knowledge it gleaned from human research papers. Then came analysis at 38.2%, and finally originality at 10.1%. This initial reliance on direct, prior examples is perfectly understandable for any learning system as it's building its foundational knowledge. It learns by seeing what's been done before.
Okay, so it leans on established knowledge to build a baseline. But what happens when you look only at the very top-performing, state-of-the-art architectures in the model gallery? Does that pattern change?
Here's the crucial insight, the second and most profound part of that pattern. For these top-performing breakthrough architectures, the proportion of design components attributed to the analysis phase increases markedly to 44.8%.
More from analysis for the best ones?
Significantly more, compared to 37.7% for other non-SOTO models. Conversely, the proportion of truly original ideas decreases to 6.6% for SOTA models versus 10.4% for others.
Less originality for the best. Interesting.
And the cognition component, while still significant, also slightly decreases for SOTA models at 48.6%.
So to achieve true breakthroughs, the AI relies more on understanding patterns from its own experiments, its analysis, and less on pure originality for the sake of novelty. It's learning from its own experience.
Exactly. This finding suggests a crucial parallel to human scientific progress. While basic competency and initial ideas can certainly be built upon direct experience and existing knowledge, there's the cognition part. Achieving true excellence and breakthrough results requires a deeper, more abstract level of understanding.
Got it.
This comes from synthesizing, reflecting on, and learning from empirical results, particularly its own. For an AI to produce truly breakthrough results, it cannot merely reuse past successes from human literature. Instead, it must engage in a process of exploration, summary, and discovery, a reliance on analysis to synthesize novel and superior solutions.
Wow.
This is perhaps the most significant aha moment for you, the listener, showing how AI is learning how to learn effectively to perform self-reflection and synthesize insights from its own trials to genuinely innovate beyond its initial training data.
It's not just doing science, it's refining its method of doing science.
That's a perfect way to put it.
That's truly mind-blowing. It's not just about what the AI found, but how it learned to find it. It's a meta-learning for scientific discovery. So looking ahead, what does all this mean for the future of AI research? What are the key implications and promising directions for future work identified in the paper?
Well, the core contribution of this paper is profoundly important. It definitively establishes the viability of this AI self-optimization methodology. It proves that an autonomous agent can iteratively discover and refine novel neural architectures to achieve state-of-the-art performance.
It works.
It works, and this opens up several highly promising and impactful directions for future research.
What's next on their horizon, building on this success?
One very promising direction is multi-architecture initialization. Currently, the ASI-Arch system starts its search from a single, strong baseline architecture like DeltaNet and tries to improve it.
Starting from one point.
Right. While effective for initial exploration, future work could involve initializing the process with a diverse portfolio of architectures simultaneously. This would not only test the framework's ability to manage more complex, multimodal searches across different architectural paradigms, but could also lead to the discovery of entirely new families of architectures, fundamentally different from anything seen before.
Discovering whole new types of AI.
Potentially. Of course, this would naturally demand a significant increase in computational resources, but the potential rewards are immense.
That sounds like it could unlock even more radical, unforeseen designs. What about understanding the internal workings of ASI-Arch itself more deeply?
That falls under component-wise analysis, often referred to as ablation studies in research. The current experiments rigorously validate the ASI-Arch pipeline as a cohesive whole, proving its overall effectiveness.
Prove the whole system works.
Right. However, due to the incredibly resource-intensive nature of each design iteration, a fine-grained ablation study where individual components of the system, like the cognition module versus the analysis module, are systematically isolated and tested wasn't performed in this initial work.
Didn't have the resources to test every part separately.
Exactly. So a crucial avenue for future research is precisely dissecting the pipeline to better understand the interplay and individual importance of its various parts. This deeper understanding would enable a much more targeted optimization of the framework itself, potentially leading to even greater efficiency, creativity, and faster discovery cycles.
Fine-tuning the AI scientist itself.
Get it.
And finally, moving these brilliant architectural discoveries from the realm of research into practical, deployable use. That sounds like the final piece of the puzzle.
Indeed, that's the engineering optimization aspect. This paper primarily focused on demonstrating the viability of the AI for AI framework, with a strong emphasis on architectural innovation and achieving state-of-the-art performance.
Focused on the discovery.
Right. It didn't extend to the often labor-intensive, highly specialized task of writing custom accelerated kernels for these newly discovered architectures, for example, using low-level programming libraries like Triton for maximal efficiency.
Making them run fast in the real world.
Exactly. A critical next step for transitioning these breakthrough designs from pure research to practical deployment would be to focus precisely on this engineering aspect. Rigorously benchmarking the real-world efficiency and latency of these models would be an invaluable follow-up study, completing the cycle from automated scientific discovery to practical, high-performance deployment.
So we've explored a future where AI can not only design new AI architectures, but also learn how to design them better, continuously surpassing human intuition. Consider the profound implications of a future where the pace of AI advancement is no longer bound by human creativity or human research bandwidth, but by the sheer scale of computation. What does it mean for human researchers when artificial intelligence can conduct its own scientific breakthroughs, discovering principles that we, with our unique human cognitive biases, might never conceive? It's a question that challenges our fundamental understanding of discovery itself.